Welcome to Dr. Boxy Teaches Electromagnetism. We are finally ready to start our study of electricity and magnetism. So let us get started. The building blocks of reality, the constituents of everything we see around us, have a property known as their electric charge or simply their charge. And it turns out that charges exert forces on each other due to this property. What we want to do is to understand this force, and in order to do this, we start with a bunch of charges. So I drew some points on the slide, and I choose one of them. Let's say this one here on the left, and I called it capital Q. We will call it a test charge, and our objective is to understand the force exerted by all the other charges on this one test charge capital Q. All the other charges, Q1, Q2, Q3, will be known as the source charges, the ones exerting the force. Capital Q, the test charge, is the one feeling the force, undergoing that force. Now, the question we want to answer is the following. Given the position, the motion of all the source charges, so I have R1 of t, R2 of t, etc., which will be the position of each of those source charges throughout time. R1 of t is the position at time t of source charge Q1, etc. Given the motion of all those source charges, what is the force exerted by all of them together on this one test charge capital Q? Now, this question turns out to have a very complicated answer, and we will build up to that answer. And to start, we will actually take in a couple of empirically known facts about reality, about this force, about charges. First of all, it is known that there are actually two types of charges. We could have called them green and blue, but Benjamin Franklin, one of the founding fathers of the United States and also a scientist, an engineer, an inventor, called one of those charges negative and the other one positive, and the convention that he introduced is still used to this day. So there are two types of charges, positive and negative charges. Additionally, there is also something known as the principle of superposition. What it says is that if we want to know the total force exerted on the test charge capital Q, we can actually calculate the force exerted by each of the source charges separately. So F1 is the force exerted by Q1 on the test charge, as if all the other source charges were not there. And we can do that for each and every one of those source charges and then add them vectorially. Now, there is no a priori reason why this principle of superposition should hold. We can think of forces where this would not be true. It's just a fact of life, an actual empirical fact. We know from experiments that it does hold for this force exerted by charges on each other. And because, thanks to this principle of superposition, we can actually simplify the question, reframe the question that we want to answer in the following way. We want to know what the force is exerted by one single source charge on the test charge. If we can answer this question, we can answer the original question above simply by taking the force of each of the source charges separately and then adding them up. Now, by the end of this course, we will have an answer to this reframed question, but that answer is complicated. If I show you the equation now, it will not be very enlightening. It is not tractable. It is much more pedagogically sensible, much more enlightening to go at it via a much longer route, which will teach us everything we need to know about electric and magnetic forces. So, we want to understand the force of one single source charge on the test charge. So we consider one single source charge and a test charge in some coordinate system with origin O. Now, the question of what the force is exerted by little q on capital Q is still very complicated. And we can simplify it even further by looking at a special case known as electrostatics. Now, the statics in this name refers to the fact that we're looking at a case in which the source charge is at rest. The test charge may be in motion, but the source charge does not move. Now, if we now define the vector r, which is the vector going from the origin to the test charge, r prime is the vector going from the origin to the source charge, and curly r, which is defined as r minus r prime, is the vector going from the source to the test charge, it turns out the force in this electrostatic case of the source charge on the test charge is given by this expression here. This expression was actually discovered or invented by Charles-Augustin de Coulomb. He was an 18th century French physicist and engineer, and we will look at this force in detail. But I also want to mention the fact that the property charge, electric charge, is actually measured in a unit known as Coulomb, named after this same French dude here. Now, what does this force tell us? What does this equation tell us? Well, first of all, there is a 1 over 4 pi epsilon naught at the front of the expression, where epsilon naught is known as the permittivity of space. It is some constant of nature, and its value is approximately 9 times 10 to the minus 12 Coulomb squared over Newton meter squared. It's a tiny number. And because epsilon naught is in the denominator, 1 over 4 pi epsilon naught is actually a very large number. In the standard units, it's approximately 9 billion. And that means that this force is actually a very strong force, and as such also very noticeable, has a very large impact even on small charges. Now, what does the force tell us? Well, first of all, there is a curly r squared in the denominator. Now, curly r is the separation between the source and the test charge. Having the square of the separation in the denominator means that the force weakens as the source and the test are further apart from each other. So for instance, it decreases as they are further apart, and it decreases quadratically, means that, for instance, if the separation between them is 3 times as large, the force will be 3 squared, so 9 times weaker. There is a small q and capital Q in the numerator, which means that as the magnitude, as the absolute value of those charges becomes larger, the force also becomes stronger. There is a curly r hat there. So what does this mean? Well, if we take the little q here and capital Q here, this is the vector, the separation vector curly r. And curly r hat is a unit vector in that direction, so it's a vector of length 1, of magnitude 1, in the same direction. And what does it tell us, the fact that that force is some number multiplied with this unit vector? Well, first of all, it tells us that the force on the test charge is along this line. But it tells us more than that. Notice that 1 over 4 pi epsilon naught times 1 over curly r squared is a positive number, is always positive. So it's actually little q multiplied with large Q that determines whether the whole number in front of this curly r hat is positive or negative. So we saw that, or we already mentioned that there are 2 types of charges, positive and negative charges. If both little q and capital Q, both of them are either positive or negative, if both have the same sign, then this whole expression here in front of r curly r hat is a positive number, and a positive number multiplied by a vector gives us a vector that still points in the same direction, which means that if little q and capital Q have the same sign, the force on the test charge points in the same direction as curly r hat, which means that the test charge is pushed away from the source charge, and thus we get a repulsive force. If, on the other hand, either the capital Q and little q, if one of them is a positive charge and the other is negative, then the product little q times capital Q is a negative number, and therefore the whole constant in front of curly r hat is negative, and so curly r hat still points to the bottom right, but the force is a negative number multiplied with this vector and will therefore point to the top left. And as such, the force on the test charge will be towards the source charge, and so it will be attracted to it. What we see is that likes repel, and opposites attract. This is built in to this expression for Coulomb's law. We want to rewrite the result we just found of Coulomb's law, and we do it in the following way. We again consider the case with a test charge and a source charge, and Coulomb's law given by this expression here. Now, notice that we can just pull capital Q, the test charge, to the front of this expression, and we can write this as Q times something known as the E vector, which is defined as everything else in this expression. So E, the vector E, is defined as 1 over 4 pi epsilon naught little q divided by curly r squared times curly r hat. This is just rewriting Coulomb's law. Now, this E vector is known as the electric field, the one that I've mentioned many times already when discussing the mathematics earlier. It is the E that appears in Maxwell's equations. So here we actually see for the first time the definition of the electric field caused by a source charge little q. Notice that the unit of the electric charge, F, is equal to capital Q times E. That means that E has to have a unit of Newton per Coulomb because it's multiplied with something in Coulomb, and the result has to be in Newton. The principle of superposition also tells us that if there are multiple source charges, we can simply add the electric field caused by each of the source charges separately. A last point about this electric field, is that we don't actually need a test charge. If you look at the definition of the electric field, the bottom of the two framed equations, there is no mention of a test charge here. There is no capital Q here. And so if we have a situation without a test charge, but simply a source charge somewhere in space, the source charge creates an electric field all around it. And that is independent of the presence of the test charge. And so the way we think about this electric field is the following. Every source charge creates an electric field all around it, the field known as the electric field all around it, given by this expression here. If there are many source charges, each of them creates an electric field, and we can just take a vector sum of all these electric fields to know the electric field at every point in space. And finally, if we then were to put a test charge into that field, the test charge will feel that field and undergo a force as a consequence of it. So in this way of writing Coulomb's law, we see that we separate basically what the source does from the test charge. The source creates a field, the test charge feels that field. On the previous slide, we considered the case where the source charge is a point charge. But in general, charges can be distributed in a continuous way. And so think of the following situation. We again take a coordinate system with origin O and some distribution of charges in space. And what we want to know is what is the electric field caused by this continuous distribution of charges on that one point in space, the field point. So to do that, what we do is we divide the whole distribution, the continuous distribution of charge, into tiny, infinitesimally small charges. This small portion of charge has a value dq, and the vector connecting it to the field point will be curly r. And the expression for the electric field caused by that infinitesimally small portion of charge is this expression, which is exactly the same as the one we had on the previous slide, except that we replaced q, the value of the source charge, by dq, which is the value of the infinitesimally small source charge. And if we then want the value, the total electric field at that point in space, what we want to do is to add all of these dE's. Now, an addition of infinitesimally small things is actually an integral. So what we're doing is we're integrating this dE over the whole of the distribution of source charge. And if we plug in the formula above, and we can pull out 1 over 4 pi epsilon naught out of the integral, and we're left with the integral of 1 over curly r squared times curly r hat dq. Now, this can still be rewritten depending on what case we are looking at. If the continuous distribution of source charge is linear, so if it sits on some line, whether it's straight or curved is not important. If the charge, the source charge, is distributed continuously on a line, we can actually look at lambda, which is by definition the charge per unit length. dq can then be written as lambda times dl prime, where dl prime is the length of an infinitesimally small portion of that line. And if we plug in lambda dl prime for dq in the integral, we get this expression. Doing something similar, but in the case of a two-dimensional distribution of charge, so think of a situation where the charge is distributed on some area, and we define sigma as the charge per unit area, dq can then be written as sigma times dA prime, where dA prime is the area of an infinitesimally small part of that total area S. And we are integrating over the whole of S, and we replace dq by sigma times dA prime. Notice the p on the first integral on the left, on the line case, is the line integral along whatever line the source charge sits along. Finally, if the charge is distributed three-dimensionally in some volume, then we define rho as the charge per unit volume. We can rewrite dq as rho d tau prime, where d tau prime is the infinitesimally small portion of volume of this source charge, and the integral becomes this integral here, a volume integral over the whole volume V of the source charge, where again we replace dq by rho times d tau prime. Let us look at an example of how to use these equations. These equations can be actually thought of the definition of the electric field. As a first example, we look at the case of a one-dimensional rod of length capital L, and it has a constant linear charge distribution lambda. So Q is the total, little q is the total charge of the rod, and lambda is Q divided by L, and we assume that it's a homogeneous rod, which means that the charge is distributed equally, homogeneously over the whole length of the rod. We want to know what the electric field is caused by this rod at a distance h above the center of the rod. So to do that, we start by taking a coordinate system, an x and y coordinate system, and we put the center of the rod at the origin of that coordinate system, and the rod itself sits along the x-axis. Now, what we do is we divide the rod into infinitesimally small portions, and the one I drew here in light blue is at a position x prime on the x-axis, and its length, its size, is dx prime. Now, what is the electric field at the field point we are considering, caused by this tiny portion of rod? Well, the answer to this is this expression here, where curly r, the vector curly r, is the vector going from this tiny portion of source to the field point, and curly r hat is the unit vector in that direction. Now, what we want to do to have the total electric field there is we want to integrate this over the whole rod. To do this, first of all, we replace dq by lambda dx prime, and we will look at the integral over the whole rod, meaning that x prime goes from negative L over 2 to L over 2. Now, we can use a symmetry here to simplify this calculation, because this is an integral where within the integral we have vectors. Curly r hat is a vector, and as we move along the rod, the angle of that vector, the orientation of the vector, will change. And so we're adding vectors that are changing throughout the integration, and that is quite complicated to do. We can do it, but it is quite complicated, and in this case, because of the symmetry, we can actually simplify it. We notice that exactly opposite, on the other side of the origin, there is an equally sized, equally charged portion of rod that causes an electric field which points, the original one pointed to the top left, this one points to the top right. And because it's completely symmetric, the horizontal component of the electric field caused by these two portions will be equal in magnitude but opposite. The original one will point to the left, the horizontal component of it will point to the left, while the new part will point to the right, and they will cancel each other out. And so the horizontal component of E vanishes. And because of that, we may as well just forget about the horizontal component of E and only focus on the vertical component of the electric field. In other words, we will only focus on the Y component of curly R hat. Now, the Y component of curly R hat is equal to sine of alpha, where alpha is the angle I defined on the figure above. We can plug this into the integral, and then we can do the following. First of all, lambda is a constant. It can be taken out of the integral. Y hat, the unit vector in the y direction, is a constant. It too can be taken out of the integral. And we can rewrite sine alpha and curly R squared in the following way. Notice the blue triangle I drew on the graph above, and I drew it again on the bottom right of the slide a bit larger. So we have the angle alpha here in this right triangle. The horizontal side of the triangle is the distance from the origin, which is x prime. The hypotenuse is curly R, the magnitude of curly R. And the vertical side is the height h. Now notice, first of all, that because it's a right triangle, we can use the Pythagorean theorem to find that curly R is equal to the square root of x prime squared plus h squared. And because it's a right triangle, again, the sine of alpha is the opposite side divided by the hypotenuse, which means it's h divided by curly R. We can plug all of this into the integral on the left, and we also took capital H out of the integral because as far as x prime is concerned, h does not change. We fixed some height, capital H. It does not depend on x prime, and so it can be taken out of the integral. So we're left with this expression here, this integral, and we need to solve it. The trick to solving this integral is the following substitution. We introduce a new integration variable, namely theta, and we define it in the following way. X prime is equal to h tan theta, and therefore theta is equal to the arctangent of x prime divided by h. And additionally, dx prime is equal to h times the derivative of tan h, which is 1 over cosine squared theta d theta. And notice within the integral we have in the denominator x prime squared plus h squared. Well, that can be rewritten in the following way. If we replace x prime by h tan theta, we can take an h square out of the brackets, and an identity in trigonometry is the tan square of theta plus 1 is equal to 1 over cosine squared of theta. We can plug all of this into the integral, and we also we adjust the boundaries of integration. So because theta is the inverse tangent of x prime over h, when x prime is negative L over 2, theta will be the inverse tangent of L over 2h, and the upper boundary of the integral will be the inverse tangent of positive L over 2h. So we get this expression here. Notice in the numerator we have 1h outside of the integral, 1h in the numerator in the integral, and in the denominator we have h cubed within the integral. And so we're left with one single h in the denominator, which can be taken out of the integral. And as far as the cosines go, we have a 1 over cosine square in numerator and a 1 over cosine cube in the denominator within the integral. And so we're left with one single cosine theta, and we get this expression here. Now the integral of cosine theta is sine theta, and it needs to be evaluated at the boundaries. And to do this, we actually will be taking the sine of the arctangent of something, and we have an identity which tells us that the sine of arctangent of anything, of something x, is equal to x divided by square root of 1 plus x squared. And plugging this into the result we find, we get this expression. So this is the expression we find for the electric field, a distance h above a rod of size L, of length L, with a constant linear charge distribution lambda. Now, what does it tell us? Can we understand it? Well, it is not a very simple expression, but we can at least look at whether it gives us what we expect to see in some extreme cases. Specifically, consider the case where h is much larger than L over 2. Let's think about what we expect to see here. Saying that h becomes very large means that we go further and further away from the rod. Now, from a very large distance, the rod looks like a point particle. And what we expect to see is therefore the expression of the electric field a distance h away from a point particle of charge lambda L. Well, let's see what we get. If h is much larger than L over 2, then within the square root, we can simply forget about the L over 2. We can neglect it. And we're left with the square root of h squared, which is simply h. That means that we get this expression here, the 1 over 4 pi epsilon remains. Lambda L in the numerator remains, but in the denominator we get an h which was already there, and we get an additional h which came out of the square root. We're left with h squared times y hat. And notice if we now replace lambda L by q, we get this expression here, and that is exactly the expression we would expect to have from a source charge, a point source charge q, a distance h away from it. So we get, at least in this limit, the expected result. We can also look at a different limit. So we go back to the result we found, which I wrote at the top left here. But this time we will look at a very long rod. So we think of L as becoming infinitely long. And what we expect to see is, well, we don't know actually what we would expect to see because we don't have an expression yet for infinitely long rods. But what do we find if we consider the case L over 2 is much larger than h? Well, in that case, in the same square root in the denominator, we can forget about the h squared term. And so we're left with the square root of L over 2 squared. So we're left with an L over 2 without square root and without the square. The L in the numerator and the L in the denominator cancel out. And the 1 over 2 in the denominator comes up. And so we're left with 1 over 4 pi epsilon naught times 2 lambda divided by h times y hat. Now, this expression, we don't know it yet, but in a couple of lessons, we will actually calculate using a very different technique the electric field, a distance of h away from a infinitely long, uniformly charged rod, and we will get exactly this expression. So keep this in mind when we go on and we see the actual expression for an infinite straight wire. Now, it won't be any fun if I did all the work for you. So here's an example that you have to work out yourself. We're looking at the same rod, but we're looking at a more general case here. The field point is now at a position capital A, capital B. So that is an arbitrary position in two-dimensional space. The question I have for you is, what is the electric field at that point caused by the rod? Now, I will give you the answer, or at least the answer as I calculated it. I found the following result. If we are not on the x-axis, in other words, when b is different from 0, I get this incredibly long and wonderful expression here, which is completely untractable. But what I ask you to do is, first of all, calculate it. And then once you did calculate it, check whether you get the results you expect to see in the case that we studied before, the one that we actually solved on the previous slides. Now, if we are on the x-axis, but not on the rod, so we look at a case where b is 0, but the absolute value of a is larger than L over 2, I get the expression at the bottom left. And if we are on the x-axis, but within the rod, the absolute value of a is less than L over 2, I get the expression I wrote at the bottom right. Now again, I ask you to actually do this. Try to find this result, to calculate this result. See if you understand what it is that we do here, and check my calculation because I may have made a mistake. I'm not 100% sure of this. And if you get stuck in this calculation, or if you make the calculation and you find a different result, please let me know. Send me a comment and I will be very happy to be corrected. Now, there is one point that I do want to mention here, and that is the following. If you notice, I considered when we are on the x-axis, the case where the absolute value of A is strictly larger than L of 2 and the case where we are strictly smaller than L over 2. I did not consider the case that the absolute value of L is L over 2, so the actual case when we are on the boundaries, the left and the right boundary of the rod. The reason for that is the following. If I look at the rod, so this is the whole rod. If I look at the case when we are within the rod, so let's take for instance this point here on the rod, the reason we can calculate it, we can calculate the electric field at that point is the following. All the points to the right of it have an effect on this point, create a field at that point, which is the same but opposite as all the points in an equally sized portion of the rod to the left of it. That means that all these points to the left of it create an electric field at the point here in question. All the points to the right of it create an electric field, and those two cancel each other out. And so the net electric field at that point is only due to this portion of the rod, to the portion of the rod further away from it, the part that is actually not cancelled out by the portions left and right of it. And so that is how I calculated the electric field at every point within the rod by simply neglecting the parts of the rod that cancel each other out. But this cancellation does not happen at the boundary, because at the boundary, for instance, if I look at the right boundary of the rod, all the points to the left of it create an electric field, but all the points to the right of it do not. There is no rod to the right of it. And because there is no cancellation happening, if you were to try to calculate the electric field at that point, what you would find is infinity. You find an expression which diverges. And so the electric field there is simply not well defined. So the reason it works within the rod is this cancellation, which does not happen at the boundary. As a second example, I also want to look at the two-dimensional case. So here is a surface distribution of charges. So I take a disk with a total charge Q, and it has a constant surface charge distribution sigma, where S, capital S, is the area of this disk, and capital R is its radius. What I want to do is to calculate the electric field at distance h above the center of this disk. How do we do it? Well, I divide the disk into sectors and I look at one tiny portion of it. I want to know what the electric field is caused by this tiny portion on the field point in question. And it is given by this expression where, once again, capital curly r and curly r hat are defined in the usual way. We can replace dq just like we did before, but this time in the two-dimensional case by sigma dA prime, where dA prime is the area of this tiny portion of area. Now, once again, what we will do is integrate it over the whole disk. Now, notice that again we have a cancellation happening. On exactly the opposite side of the disk, there is another portion which creates an electric field whose horizontal component cancels the one that the original portion of area created. So once again, the horizontal components of E vanish, and therefore we will be left with a vertical component of E only. And if we define an x, y, and z coordinate system, what we're looking at is basically the z component of the electric field. So that is the only one we need to consider. So the electric field will be the integral of this expression, but where we forgot about the y and x components of curly r, and we're only looking at its z component. Now, if I define the angle between curly r hat and the z-axis as gamma, then the z component of curly r hat is the cosine of this gamma. And as we saw in polar coordinates in one of the previous lessons, the tiny portion of area dA prime is equal to rho prime d rho prime d phi prime, where rho prime and phi prime are defined in the same way we did in polar coordinates, namely rho prime is the distance from the origin to this portion of area, and phi prime is the angle between the positive x-axis and this portion of area. We plug all of this into this double integral, and notice the double integral goes over rho prime and phi prime, where rho prime goes from 0 to capital R, the radius of the disk, and phi prime goes over the whole circumference of the disk, in other words, from 0 to 2 pi. So this is the integral we want to calculate in this case. How do we do it? Well, we look at this blue triangle here, and I drew it again here. It is once again a right triangle. Its horizontal side is rho prime, the distance from the origin to the portion of area in question. The hypotenuse is curly r. The top angle of it is the same gamma we defined earlier, and the vertical side is h. And we want to rewrite the cosine of gamma and curly r using this. So first of all, just like we had before in the one-dimensional case, curly r can be calculated using the Pythagorean theorem, and the cosine of gamma is h divided by r, by curly r. We plug all of this into the integral, and we find this expression where, notice also that the rho prime integral and the phi prime integral are independent of each other, so we can factor them. And if we factor it, we are left with two integrals where the phi integral, the phi prime integral, can be calculated immediately. So it's simply 2 pi. This 2 pi comes out of the integral and cancels with the 4 pi in the denominator at the front, so we're only left with a 2 in the denominator. And in the second, in the rho prime integral, the h can come out of the integral, and we're left with this expression here. And this is the integral we want to calculate now. To do that, we use the exact same technique we used for the one-dimensional integral. We use this substitution, and the rest of the calculation is completely analogous to what we had in the one-dimensional case. I wrote it out here. I will not go through the details. If you want to look at them, take your time, pause the video, and look at them. They are identically the same as what we did earlier. And we get this result for the electric field. Now, once again, what I leave to you here is to actually check whether you get the result you expect. So for instance, you take the disk, and as h increases, as you go away from the disk, you would expect the disk to look more and more like a point charge. Look at whether you get the electric field of a point charge as h becomes larger and larger, as it becomes much larger than r. Check those results. Check my calculation, make sure you understand everything that happens. This is what I wanted to tell you about the electric field itself. In the next lesson, we will look at something known as Gauss's law and the divergence of the electric field. I will see you then.